There you go.
Thank you. Okay. Confidence.
Yeah, confidence. Ooh. Okay, so I did my poster project on the aqueous ferrofluid lab that we did, and to first get a good read on the aqueous ferrofluid lab, you have to first understand what a ferrofluid is. And so a ferrofluid is a colloidal suspension of magnetic nanoparticles. So what is a colloidal suspension? Well, you have solution and you have these very, very small nanoparticles. And the nanoparticles have to be within a certain range of sizes to become the colloidal suspension. So all these nanoparticles are magnetic. Okay, so now you know that these nanoparticles, as they decrease in size, will show an increase in reactivity as well as more effective surface effects. So if you do anything to them, it will increase those effects. So if you didn't really understand that, here's an explain like I'm 5. Ferrofluids mean that you have a bunch of really small things that interact with magnets. This kind of magnet is special because it moves in the liquid state like water. Solid magnets can't do that. So some examples of ferrofluids, of aqueous ferrofluids, are gold-coated iron and iron 2 oxide. Fe3O4, which is iron oxide, that uses both iron 2 and iron 3. So who first discovered aqueous ferrofluid fluids? Aqueous ferrofluids were first discovered by and invented by Stephen Papel, a NASA scientist that worked for the purpose of rotating shaft seals in satellites in space. So this was done in the 1960s, and since then it's been growing continuously. The importance of aqueous ferrofluids is great because normal solid magnets, once you heat them up enough, before they can turn into a liquid state, they reach their Curie temperature, which means that the heat energy they have is so great that it scrambles all the atoms so that they cannot line up for their magnetic lines. So magnets, they're at that temperature, at the Curie temperature, they're no longer affected by magnets, and so on. So an example of that is Earth's core. It's molten iron, as we think, and it can't be affected by our north and south poles. So a few applications of this aqueous ferrofluid belongs in magnetic carrier technology. So this carrier technology is like, electronic appliances we use every day. As well as identification purposes for money. So to make sure that you don't have counterfeit bills, you can lace your currencies with the aqueous ferrofluid so that your currency reacts with this metal. With magnets, sorry. Aqueous ferrofluids can be used also as ink for jet printers, so you can have this awesome magnetic text for your paper. So, along with this, you can also use it for data storage because as these nanoparticles decrease in size, since they're very small, they can exhibit, they can store memory with, on and off states. So the procedure that we had in class was a thorough one, but somewhat simple. So when we started with a 100 milliliter beaker, and into it we added 4 milliliters of iron 3 chloride and 1 milliliter of iron 2 chloride. So we mixed the solution, and after mixing it, we began dropping in 50 milliliters of ammonium hydroxide over a period of about 5 to 10 minutes. I took about 10 minutes, if I'm not mistaken. And once we finished that, the solution began turning dark, and that was basically the formation of the Fe3O4. So to understand what's really happening in everything, we should write down the equation that describes this. So what's happening is we have two molecules of FeCl3, right, with the addition of one molecule of FeCl2 and 8 molecules of NH3, as well as 4 molecules of H2O, forming one Fe3 molecule, well, Fe3O4, so our aqueous ferrofluid that we created in the lab, and 8 molecules of NH4 chloride, so ammonium chloride. So in the first two steps, we had iron 3 chloride and iron 2 chloride, missed 2, and we added our ammonium hydroxide. So this ammonium hydroxide was in a water solution and as such dissociated. So we had NH3 and our water. Okay, and this created the iron oxide. So once we finished that, we decanted as much of the excess liquid that we got from steps 1 and 2 into another 100 milliliter beaker to be left with the magnetite solid. So after that, we transferred our remaining solid into a weighing boat, well, solution, sorry. And to make sure that we got all of that solution, we put in some ultra pure water and rinsed the 100 milliliter beaker. So with that, we then put a bar magnet, since we created our iron oxide, which conforms under magnetic, magnets, and we condensed all of that iron oxide at the bottom of the weighing boat. So we were left with the ultra pure water that we used, as well as the excess liquid that we got from steps 1 and 2, anything that was left. So we again decanted that, and to make sure that we had a clean solution of iron oxide, we rinsed with that ultra pure water again and used the magnet to decant the ultra pure water. After this, we removed the bar magnet and added about 2 milliliters of what I like to call TIMA. So that's tetramethylammonium hydroxide, and this acted as a stabilizing agent for the iron oxide that we used. Without it, it would aggregate, the iron oxide would aggregate and just not be that liquid magnet that we want it to be. So we removed the bar, we added the tetramethylammonium hydroxide, and we then attracted the now ferrofluid, like since we added the tetramethyl ammonium hydroxide, with a bar magnet again, and decanted all the remaining water, which was now dark, from the solution. So this dark water was not only the remaining Timmy, but remaining like iron oxide that we did not need. So after that we again decanted and so on and so forth, and we continued doing that until we had a very clean solution of the ferrofluid that we needed. And by using a cow magnet and placing it under the weighing boat, we could observe the effects of the magnet on the ferrofluid. So our result was this ferrofluid solution, and unfortunately I didn't have a picture of my own ferrofluid, but my ferrofluid did not entirely work, and it was very unresponsive to magnets. So I drew this like very linear solution with a few bumps in it. What we should have observed after finishing it and placing the cow magnet looked just about like that. So as you can see, this is the positive end of the magnet, and it was receiving the force from the negative end, and it created like the lines from magnets. So it creates a magnetic force that comes from the negative and ends of the positive in a angular fashion, and that happens several times, which is what happens with the aqueous ferrofluid. So on a nanoscale, I know it's a very small picture, but all the ferrofluid, the iron oxide that we made, looked like very large balls of about 50 nanometers. So this was the ideal range for our colloidal suspension, and that was our result. So as a conclusion from our results, we can learn that the concentration of the ammonium hydroxide is why the particles, the nanoparticles that we created, are the size they are. And by altering the concentration, you can also alter the size of these ferrofluid nanoparticles. So that is one of the things that you can do for the future. You can modify this ammonium hydroxide concentration to focus with the data storage by making the ferrofluid nanoparticle size smaller. You would have an inversely proportional effect to the amount of data storage you have. So by making the particle size smaller, you have increased data storage. So this is what Vaishnav's and Meg's results were, and that's basically what mine were. So to improve this experiment while doing it, I thought of having two people instead for steps 1 and 2 of the procedure. So one person would stir the solution vigorously and continuously, while the second person added the 50 milliliters of NH4OH, the ammonium hydroxide. And the person that would be stirring vigorously would be counting how many seconds have passed, and told the person putting in the drops when to drop it. So with this two-party system, two-person system, you have a more accurate dispersion of ammonium hydroxide into the iron 3 chloride and iron 2 chloride solution. And with that you'll have better iron oxide nanoparticles. So yeah, thank you very much. That's my presentation, and I was wondering if you had any questions.
Thank you very much, Yev.
I have a lot.
Very nice presentation. Do you want to get started, Bush?
A lot of questions
Actually, just-
from my buddy here.
Before you get started, I like your idea. Leave it open. I like your idea for the future experiment with working in pairs, but actually we also have some new equipment in the lab. I think Nicole ordered something called a burette that could make it a lot easier.
Yeah.
So just put it in a burette and just open it very slightly to control the drip rate.
Yeah.
While stirring it.
That
If we had those before, then that would have made probably a lot easier for this experiment.
Yeah, I was thinking of working with just what we had before.
That's true,
The pets and.
That's definitely a
so
good idea, because it's hard to continuously stir and very carefully add drop-wise the ammonium hydroxide.
And watch the time.
I'm sorry?
And watch the time.
Exactly.
Yeah. So with an increase in funds, so that would be easier.
Exactly.
Okay.
But you want to get started?
So, why does more capping substrate make it smaller?
More capping substrate.
Which is the NH3, right?
The NH4OH, yeah.
NH4.
NH3 is, well, the ammonium hydroxide, yeah, provides the ammonia, and the NH4 plus is a positive charge, while the iron oxide was surrounded by a negative charge.
Wait,
Barely
the
seen.
iron oxide, wasn't it like a combination of the FeO2 and the FeO3?
Yeah, so
And then that has to be
the
capped,
product,
right?
iron oxide, right, is a simplification of your +2 iron that you had at the start, 1 oxygen, and 2 iron 3s, and 3 oxygens. Since your oxygens always have a -2 charge as their oxidation state, you have to shift accordingly with your positive atoms.
So going back to the capping substrate.
Yeah.
So how does that?
So by increasing your NH4OH, your ammonium hydroxide, you have more ammonium hydroxide to just surround it with. So imagine you had a sphere, right? That's 1 iron oxide nanoparticle. You have just enough to cover it, right? But if that were to split apart, right? Here we used about 9, right? You'd have enough for 8, and then you have 1 extra ammonia. So that's left for the second sphere. But you need more of that capping agent, that reducing agent, to surround the second sphere. So with that, you would have enough to reduce your nanoparticle size. It's basically the factor of the size. So.
Alright.
What did you say the capping agent was?
The stabilizing agent is the tetramethammonium, and the capping agent was the ammonium hydroxide.
I think the stabilizing agent should be the same thing as the capping agent, actually.
I see.
Yeah.
Okay.
The ammonium hydroxide would have had a different role.
As a reducing agent.
Exactly.
Okay, sorry.
It's okay.
The ammonium hydroxide was a reducing agent for the two.
For the size, and the capping agent, the tetramethammonium, stabilized the size so that it wouldn't shift.
Ammonium,
Sorry.
which is, could you draw the molecule for that?
the molecule
I mean like the formula.
for
The tetra.
The
tetramethylmonium?
Yeah.
Okay, so I'm gonna have to erase a few things here. So
Um,
so tetra means 4 in IOPAC language. So you have your 4 carbons, and they share, bonds. And at the end of your carbon chain, you have an ammonium. So NH3. Well, in our case, NH4 plus OH with an OH. So it would have 4 electrons and 1, 2H, 3H, and then an OH. So to all these you have, hydrogens. Those are hydrogens. So that's your tetramethylmonium, I think.
so
Okay.
this. Alright. I'll just go to the next question. So why was yours so unresponsive?
Mine was unresponsive because at the step 2 of the procedure, where you have to stir the solution continuously while adding the ammonium hydroxide, I had spurts of ammonium hydroxide where I would not put enough ammonium hydroxide, and then I would just lose track of the time and then realize that I wasn't going with pace, so I would put too much ammonium hydroxide afterwards.
So do you
And it
think
would-
your
Keep going like
conglomerates of this this Fe2O4, right?
Fe3O4.
Fe3O4. Were they too big, or do you think they were too small?
Well, because for my failed experiment,
Mhm.
for my failed experiment, I would think that they would be too big, so too much of it aggregated, and so on throughout the procedure.
And so what exactly happens? Why is it like spiky?
Well-
Why is the when you put a magnet under it, why does it give that spike shape?
Well, again, that goes to the way the magnetic waves go from a negative end to a positive end. So they go at that angular way, and that goes everywhere, like
So it's
the
like
Earth.
going out.
Yeah, from the south to the north.
Like,
It goes outwards and then back inwards. Like a very distorted, convoluted sphere or oval.
I see that.
So because this is, aqueous, it's going to follow those lines, because that's how the magnetic waves are. It wouldn't just stay how it is. Otherwise, it wouldn't really be magnetic.
Right. And one last question.
Okay.
So how exactly is the magnetism working here?
The magnetism?
Yeah.
I'm afraid you have to elaborate on your question a little bit more.
Sorry. So the Fe3O, are you Fe3O4?
Yeah.
So how exactly is what propagates the magnetic properties of that molecule, or like is it a conglomerate,
Well-
or is it like a bonding between the oxidized Fe2O3? No, FeO3, right?
Okay, so I still have a little bit of the equation left.
Yeah.
You started with FeCO3.
Yeah, so you
And
have
FeCO2.
Fe3 minus 3, right? And then
Fe3 plus.
3 plus, yeah. And then Fe2
2 plus.
plus. And then that turns into FeO3 and FeO2.
No.
No?
Because oxygen is always going to be a 2 minus when it forms. Like, so you have H2O, you have SO2, where sulfur is having a 4+ oxidation state. In this example, you have Fe2O3 and FeO, where in both cases oxygen is 2-, and your iron is going accordingly. So that metal property you were talking about comes from the iron, right? Most metals, or all metals, I think, exhibit metallic property at certain temperatures, below the Curie temperature, which I talked about. And yeah, so your iron, since it's in a liquid state, will still exhibit that metallic property. Okay, I hope that was not too confusing. Yes?
And back to his earlier question about, did you think that your particles in your colloquial suspension were too big or too small? You said in there that the optimum size was about 50 nanoparticles.
Nanometers.
Nanometers. Sorry. If it is smaller than 50 nanometers, what would you say? And if it was larger than that, what would you say? Would you be able to distinguish between them, and would your experiment fail for different reasons and in different ways?
If they were too small, if they were about below 10 nanometers, I think, you would have a solution. And if they were above 100 or 150 nanometers, I'm not too sure, you would have a I can't quite remember the word, but the different sizes in nanoparticles would give you different things. Like if they were above colloidal suspension, right, they would aggregate more. They would sink down to the bottom of their suspension, basically. They wouldn't be suspended. They would just fall down and then precipitate. Yeah. So, if they were too big, your magnetism would degrade pretty quickly over time. If they were too small, I don't really know why, what would happen, since since they would have an increased effectivity for data storage and whatnot, and they would have effective surface effects. But my guess would be, if these ferrofluids were so small that they created just a solution, they wouldn't really have an effect on their solution. It would just be slightly magnetic, if that makes sense. I'll have to look.
It wouldn't be able to like pull up, so like with such power.
You would still have the same amount of molecules of iron oxide. So I'll have to look into that.
Now, I'm still trying to picture a fluid magnet, which is essentially what you're talking about.
Yeah.
In a traditional solid magnet, I have a negative end and a positive end, and it's solid, and pretty much this side of my magnet is negative, and this is positive. I bring another magnet and it attracts and repels, right?
Yes.
In your solution, which is basically what you're looking at, right? Is it that if I were to put it in the water bottle, for example, there, would one side be negative and one side be positive of that whole water bottle? Or are you really talking about ionic particles floating around there with each one of them being positive and negative on a different pole, such as what you drew in your little particle?
Well, since it's the iron that displays the magnetism, and since it's a liquid, the ions can easily shift themselves just how they want to align themselves with the magnetic
Field lines.
fields.
Field lines.
So it's more like when I
Lines.
have the small
rays.
iron particles and I pull the magnet and I can see how they shape and I actually see the
I wouldn't.
field.
I don't really know what would happen if you put it in a water bottle, assuming it's ultra pure water. But
I was thinking-
since we were decanting ultra pure water, I would assume it just gets in the way of your magnetism and yeah, it wouldn't be very magnetic. It has to be a very high concentration of
So
this.
it's not so much that one side of your container was positive and negative as in the solid. It's more like when you're dealing with those iron shavings that we're
Exactly.
putting on there and we're actually turning them around and they're moving and they're lining up is more.
Yeah.
And that's what you're actually seeing there, or what you were hoping to see, is more equivalent to when we pull a magnet and we line up those iron
Exactly.
shavings and we make that.
Yeah,
That makes
because
more sense to me.
explain what happened. I think you guys tried this. What happened when you flipped the cow magnet? So you tried it from the negative side, or the North Pole, and then the South Pole, or at least on the ones that worked.
If I recall correctly, what happened was just the waves either just shifted or were the same, so they just shifted in where they were, and it maintained like the wave, the
So it was still,
magnetic
it was
field.
still the same spikes, though, pretty much. Right?
Yes.
Yeah.
It was just flipping. You
Yes,
couldn't really
since they-
see it, but what happened is in one case you had the negative poles of the
That
the
particle-
the
iron
particles
oxide,
actually popping up, and the other side you were seeing the positive poles were attracting
Yeah, since
towards
they
you.
can easily align themselves.
Got it.
Just-
Okay.
It's just a matter of shifting the molecules.
What would happen if you dropped the magnet in it?
Ooh, since it's
Okay.
attracted to the magnet, I would assume it just surrounds the magnet completely. It would be a very good way to decant because since it's
Go
just
together.
strongly attracted to the magnet. But since it's in this liquid phase, it would be a very, very painful way to scrub it off.
What's keeping them separate? Like, if I had two of these iron nanoparticles, essentially, right?
Yes.
This one has a positive end and a negative end, and this one likewise, right? Of the individual nanoparticles, correct? They're easily able to float around and change their direction. So what is to prevent this positive end coming over and being attracted to this negative end and end up basically with it all congealing together? What's keeping them separate from each other?
Well, the tetramethylammonium hydroxide was added in to surround all of the iron oxides globs. Like, it's not just singular, atoms. It's globs of these Fe3O4s, and the capping agent provides the
The coating.
the coating to repel these nanoparticles from each other, so that they don't align themselves.
What do you think would happen with your Fe3O4 if you use different ratios of the initial FeCl3 and FeCl2?
Well, the iron 3 chloride and the iron 2 chloride were in a specific ratio to create our Fe3O4, and if you switch those ratios, since the iron 3 chloride and the iron 2 chloride were already solutions, if basically what would happen was you have a certain amount of reactant and you have a certain products that come from that. If you switch the ratios, then either the iron 3 chloride or the iron 2 chloride will become the limiting reactant, making the amount of product that you make less. Lost my train of thought, but by switching the ratios, you would just have less product and the reactant would be decanted along with the rest of the excess liquid. So you just have less product as a result. That's
Okay.
the only thing that would change.
And sort of like as a follow-up to Rita's question, what, this is also a little bit beyond the scope of the class, so it's okay if you don't have an answer, but what type of magnetism is exhibited by these magnetite nanoparticles?
Well, I heard that it was mentioned in this room as I was walking away.
I mentioned
It was super
Para.
paramagnetism.
Something
But-
like that.
And how is that different from like magnetism that, for instance, a refrigerator magnet has?
Well, my guess would be that
For instance, let's say you had this
Yes.
ferrofluid, and you
yes.
put it up to a refrigerator. Do you think it would?
Okay.
Do you think it would stick?
I would. That's a very interesting question. I would think that the nanoparticles would align themselves with the refrigerator magnet to like stick and then slowly slide down.
But what if they're so like the refrigerator itself
because
isn't
of gravity.
really like the thing that makes the magnet stick to the fridge is the magnet itself, like the refrigerator magnet, not the refrigerator, right? So like the magnet itself you can see is that black magnet usually,
Yes.
and that's what sticks to the fridge. But if you put another piece of like another piece of steel, for instance, up to the refrigerator, it won't stick.
Oh, okay.
So the refrigerator is not what's called ferromagnetic, which
It's ferric magnetic.
not exactly.
Okay.
But
Sorry.
forgetting about that, so with that being said, do you think that the ferrofluid would stick to the refrigerator?
Well, since they're different kinds of magnets, then I guess we just slide down and then plop on the floor
Yeah.
and not stick at all. Okay.
Or
I
would it
think-
be because of like would it happen because of the small like since it's so small it couldn't like support itself with all that like maybe like some of that fluid if it was like in a fluid form couldn't support itself so it like slowly seep downwards.
Sort of, but the main thing is the refrigerator and the ferrofluid are both examples of what's called paramagnetic magnetism. So they don't exhibit their own magnetic field lines like what you have drew on the board. They only respond to magnetic fields. So their magnetic dipoles will align with the magnetic field lines, which causes that strong attraction. But the ferrofluid doesn't have its own magnetic field lines coming out of it, so it's not
Yeah,
like
it's from the cow magnet that's
exactly.
being put.
So it's not like the ferrofluid could stick to something that's that's not another ferrofluid, or that's not another ferromagnetic material.
Mm.
So you
So similarly another fridge can't stick to another fridge.
exactly.
Sticky
And
edges.
like the reason to this is all like quantum mechanics and way over our heads. So let's just end it with that.
Alright, I think.
So, very nice job.
Um,
Does anyone else have any questions? Okay,
Okay.
so good job, guys.
Yeah.
You can help turn it off.